Hello, everyone. We are going to talk about AC circuit, which is chapter 15. So here we are going to solve some of the problems when VT or IT is going to oscillate. And then we note that resistance does not have any frequency dependence, but there is a XC, XL, and then it is given by omega C, is given by omega L. And then we have an impedance, which is given by R square plus C minus XL square squared. Okay. So this is the very important one. And then if you have an impedance, then it works as a kind of a resistor, so that the Ohm's law for AC circuit becomes Z. Okay. Or you could say that I is given by V over Z. Okay. And then we have a interesting case for the resonance. We call it the resonance. And then there is a omega resonance is given by Z. Okay. And then in the resonance, your current shooting up as a function of omega, and then this is the resonance. Okay. So this is the background, and then let's try to solve the problem. And so, oops, I have to erase this one. Setting is a little bit strange, but anyway, let's start the problem 51. So if you look at it, there's a LC circuit with the L and C, and it's driven by an oscillator source of EMF. Okay, so there is a AC source, and EMF is given by is sine omega t. So Emax is given by this one, and the omega is known. What is the peak? What is the? We need to find out. Peak instantaneous current across the capacitance. Capacitor. That's the problem. So we have a ideal driven as circuit. So that in this case, note that R is 0. Okay. And that's we have this EMF, which is the voltage. And then the current amplitude is set by the reactive impedance such that we have a L and C, and we have a capacitive reactance and inductive reactance, which is caused by inductor and capacitance. Okay, and then what we have to do is to just plug in those frequency, angular frequency, and resistance, the inductors and the capacitance value. You get this value in terms of ohm. And then the net reactance of a series of LC is given by XL minus XC. That is the thing we need to consider. And then the peak current is given by Ohm's law in AC. So this is the case. Note that G is, in this case, X, because we don't have resistance. So only the reactance and capacitance is the main source of Ohm's law. Okay, and then if you just plug in those values, and you will get the current in ampere. Okay. So basically, it is chapter 15 and the chapter 16 is rather easy if you try to memorize the formula and then plug in the numbers, and you will get the right answer. So most of the problems in the exam 3 is basically plug in the formula. So you have to pay a lot of effort to memorize the formula. Okay, so resistor and the capacitor are connected in series across the AC generator. So that EMF is given by, voltage is given by this value. It's AC. And here is the resistor and the capacitor. So that we need to find out the impedance of the circuit. Okay. So we have a voltage is given by this one, and the R resistance and the Z, and we want to find out the impedance Z of RC circuit. So in this case, it is absolutely important to know what is the omega, the angular frequency. So we have this. From this, you get this omega. And then once we get the omega, then we can find out a reactive, capacitive reactance given by this one, so that we get this value for the capacitive reactance and the impedance formula for the RC series. So note that initially and then we don't have any XL is given by omega L, and we have L equal to 0, so that the only term you have is XC squared. Okay, and then we get R in ohm, XC in ohm, and then we can find out XC is actually this value. And then we can find out the impedance. Okay, so once again, you need to notify what is the given parameters. So note that probably one of the important steps here is that it should be omega in radian per second, not the frequency, not the hertz. It should be converted into radian per second. So that is the key point. If you get the wrong omega, then everything is screwed up. So now we have a RLC series circuit. And what is the amplitude of a current in the circuit? The source are 100 volts and 50 hertz. Okay, so that the frequency is given. So note that frequency is given and amplitude of a voltage is given, and then we have a R, L, C. So note that C is given in microfarad and should be converted into a farad. This is the very important step. Otherwise, you will not get the right answer. And we want to find out the amplitude of the current. And the relation between the current, amplitude, and impedance is given by, as you know, I'm just repeating once again, it's given by Ohm's law in AC circuit. And the important thing is that Z is given by 3 terms, R, L, C. And then it is absolutely important to find out what the omega is. Okay. And we have to find out omega is 2 pi f. This is the important things. So this is, and then you get the radian per second. The reason why is that if you think about sine omega t, so omega has a 2 pi radian, and then for the given period of time, and then 1 over t is 2 pi f is actually omega. Okay, so that's the key thing. To that frequency and period is given by this relationship. So anyhow, this is another step, important. Okay, and then you know what the omega is, and then you plug in this omega to XL and XC. And then you can find out the Z, and XL is given by this one, XC is given by this one, and the XL minus XC is given by this one. Then Z is given. And once we find out Z, the I can be found out by Ohm's law in AC circuit, and then you get it. So once again, it starts from the given parameters, and then you need to know the frequency should be changed into radian per second. That's one thing. And your capacitance or Henry or ohm should be in the right unit. Ohm, Henry, farad. Okay, so it should be converted, whatever it is. And then next thing you need to think about is that current is given by this formula, and then impedance is given by this. And it is important to find out this omega, the angular frequency, and then angular frequency is given by 2 pi f. Okay, and then it's relatively easy. Once again, it is based upon very simple formula, and then you need to plug in the right numbers. Okay, and now let's try to think about the voltage and the current. So note that this voltage, Vt, and IT is given. Okay, so it's a kind of a sinusoidal function. Okay, and note that Vt is proportional to cosine omega t. And if you look at it, it is a stop from the zero, so that it should be sine omega t. So note that this is cosine and this is sine, so that it's not in phase, but it is the phase difference is pi over 2 or 90 degrees. So in this case, this is the typical example of pure inductor cases. So that you have a oscillating voltage, and then you have only one inductor. Okay, so that means it is okay. So in this case, we have voltage leads the current or current lags. Okay, and then in this case, relationship between the voltage and current is given by this one. Once again, it's the same Ohm's law in the AC circuit. And then in this specific case, we have only pure inductor. So that R equal to 0, C equal to 0, and then we get this one. And then what you have to do is that we need to find out, so again, it's given by uh, here is the case, and then it is VP is given, IP is given, and then from the this relationship, we can directly calculate the XL. In other words, inductive reactance XL, and then from this you can find out XL is already known, and then it is given by omega times L. And it is, once again, necessary to find out omega. And once again, it is 2 pi f frequency. Okay. So we know what the omega is, we know XL is, and then it is inductance is given by XL divided by the omega. XL is known, omega is known, then we can find out the inductance. Okay. So once again, it is very simple formula, and then you need to plug in right numbers with the important conversion. In this case, once again, is frequency and the angular frequency conversion is a key. And now it's time to think about the following graph shows the voltage and current through a single circuit element. What is the frequency of the AC generator, VP, and IP is given, and the T1 is given. And this problem is simple, in fact, very simple, but it does not require any type of a further investigation. Only the T1 is given, and then you need to find out the frequency. Okay, so so VP and IP is given, but the T1 is given. Okay, and the T1 is here. So one period. This is the t. From here to here is t. And then there is a half t. Okay. So t1 is corresponding to 3 over the 2t. Okay. So one period and half period. So t1 is known, and we need to find out t, the period, and that period and frequency is given by this inverse law, and then we can find out what is the frequency. So it is very simple questions. Once again, it is asking you whether you understand the AC nature. so that we have a frequency and a period and how to convert it. Okay. And next one is 150 ohm resistor is connected in a series with a capacitor. So that is RC circuit. Okay. So voltage across the resistor is given by this AC. So this is the omega is directly given. Note that omega is in the unit of a radian per second. And what you might be confusing is that the frequency is given in terms of a hertz. And then omega should be, once again, 2 pi, this is the radian, times f. F is 1/second. So you get radian per second unit, okay? So let's try to what is given, what are given. The resistance is given, capacitance is given. Once again, all the units should be changed into standard unit. So microfarad should be changed into 10 to the minus 6 farad, okay? And then our voltage is given like this. And thus the maximum voltage across the resistor is the amplitude, okay? And then angular frequency is given. And we want to find out voltage across the capacitor, VC. So we want to find out what is the VC. And for the resistor, is given by this one, by Ohm's law. And then we can find out is current is given by VR over R. Okay, so VR is given here. And its amplitude is given by this one. And then current amplitude will be found out utilizing this Ohm's law at the resistor. And then capacitance, capacitive reactance is given by 1/omega C. Okay, Xc is given by this one. And then for AC circuit is Ohm's law version. We call IR, but in the case of capacitance, capacitance reactance is given by this one. So that we know the I from the resistance. And then Xc is 1/omega C. Okay, so we can just plug in these numbers, and then it's given by this one. So voltage relation in the series RC circuit is given by this one. You note that, okay? These are the important step we have utilized. So in other words, it has the same current, okay? And then so that we found out I from the for the given VR, and we plug in the I from this resistance current, and then we get voltage in the capacitance. That's the logic of what following. Okay. In a series RLC circuit, now we have a RLC circuit. The applied voltage has a maximum value of 140 volt and oscillate the frequency over 35 hertz. So note that this is not the omega. This is the F, okay? And from the F, you should, omega is given by 2 pi F. That is the important step you should not miss. So let's try to find out what is given. So first thing is that angular frequency, omega is 2 pi F. So we have a frequency, 35 hertz, and then we get omega. Okay. So here Vmax is given and RC is given, and then we want to find out L. So note that it is starting from RLC circuit. Okay. So R is given, C is given. Note that this conversion is important. And omega is given. And then we need to find out what is it. Okay. So first one is a capacitor reactance is given by this one, and axis is this. And the phase relationship in an RLC circuit is that the phase angle between the source voltage and current is given by this relationship. Okay, so if you look at it, so tangent phi is voltage and the current, Vmax, this is VR, and then VR is parallel to the current. Okay, so that the phi here is given by this one. So here XL is given by inductive reactance is given by omega times L. So what is known here is that zeta is given. If you just look at it, the phi is the current and the voltage, current and voltage. Note that resistance, current, and the voltage at the resistance is parallel. There's no phase delay. Okay, so that the current and the voltage make an angle. This is the very important step you need to understand. Okay, and then phi is this one, but only the zeta is given. So if you look at it, this is 90 degree, so that phi is given by 90 minus zeta. So phi is 90 minus zeta, and then zeta is given by 30 degrees. So zeta is 60 degree, so that mm, oh, I'm sorry, this is okay. And then eventually phi is minus 30 degree, and then you get the tangent phi is given by this one, and we know what the xc is, and then we know omega L, omega is given, and we want to find out L. That is R omega xc is 1 over omega c. Everything is known but L. Okay, so we can just find out the relationship, and then the L is given by this one, and then we can find out what it is. Okay, so from this we can find out XL, and then from this XL we can find out L. Okay. So in this problem, what was important thing is this formula. And also, what was also important thing was the relationship between the voltage and the current is found here, right here. So that only the zeta is given. Zeta is 60 degree. And then we need to find out how to find out phi here. Okay. And then from the phi, you can get the XL, and then you can get the L. Number 66, find the maximum voltage across the resistor. Now you want to find out resistor. In RLC circuit, the voltage across resistor, and then it has R is this is microfarad, should be 10 to the minus 6. And omega, here is the omega. Omega is given, and delta V max is given. Okay, so what do we have? Okay, R, L, C, omega, and the maximum voltage. And we need the maximum voltage across the resistor. And then, to do that, we have to come up with the current. And then, to find out the current, we should come up with a total impedance. Impedance is given by this one. And then omega is known. Yeah. L is known, C is known, then we know all the XL, XC as well as the R. Okay, so we know the impedance is about this much. Okay, and then next thing is that the total current through the RLC circuit is given by this Ohm's law in AC. So we now know the Z, Vmax is given, so that, and then we find out I. And for the given I, we just plug in Ohm's law at the resistor, and then we can find out the resistor voltage, VR. Okay. And now let's try to think about an ideal step-down transformer. Transformer is a kind of devices, and then it is connected by magnetic material. So there is a NP primary, and then NS turns, and then we get the VP and VS. And in this case, we have also the resistor, and then we get the IS. Okay, and what is given is the primary number of turns and secondary number of turns, and then we get the primary voltage, and the primary current is given, and we want to find out the secondary current, IS. Okay, what is IS? And in order to find out IS, we need to find out, first of all, VS. VS is given by this relationship, or VS or VP is NS over NP. This is the transformer voltage formula. And then we get VS. Okay, this is the important one. And then once we get the VS, and also we have another important formula, this power conversions, so that conservations. So VP IP is the power at the primary coil, and VSIS is the power at the secondary coil. And then now we know that VP, IP, and from this we get the VS. And then we can find out unknown IS. Okay, so yeah. Okay. So it's a transformer formula is basically you have utilized two things, the voltage, one, and then here is the power law. Yeah, we have two equations, and then you can find out unknowns. Okay. This is the step-down transformer. Voltage decreases. So note that it was 115 volt. And then if you look at it, Vs is going to be this one. So Ns was 34 divided by 620. So it's much less than 1. Okay, less than 1. So that means Vs, secondary voltage, is less than primary voltage. So that it is a step-down transformer. Okay. And another one, there's a plug-in transformer, like this one. And then let's try to find out what is given. Secondary voltage, output voltage is given by this volt, and the secondary current is given by this one, and then the primary turns is this, and then NS this one, and then we want to find out primary current. For the ideal transformer, we have this voltage relationship, and we have also a power relationship. Okay, and what we want to know is IP. Okay, and the IP is given by this simple law. Okay, and then from this, and if you look at it, Vs here, Is here, but we do not know what the Vp is. And then the primary voltage can be found out from this. Vp is given by Vs minus P. So Vs is known, and P is known, and S is known, so the Vp is known. So we get Vp here, and then we can get the primary current. Okay. So transformer formula is basically those voltage relations and then power conservations. Usually that's the case. And from this, you get rid of the two unknowns for two equations. So in this case, Vp was not known, and then Ip was not known, so that we can get the Ip. Okay. And next thing is resonance. So variable capacitor in the tuner of a AM radio has a capacitance of this picofarad. When the radio is tuned to a station 870 kilohertz. So note that this is the resonance in the LC circuit. Okay. And then note that LC circuit has a L and C. So in this case, we have a certain resonance frequency. Resonance frequency is given by this one. And then we get this relationship such that you get C is given by this one. Okay. And this is the logic we are going to find out. So in a radio tuner, the inductance is usually fixed, and the station is selected by changing the capacitance C. So note that this is the variable. So in other words, if you think about it, C1 over C2 is given by this one, so this is a variable. So C2 could be changed. Note that C1 is given for the frequency 1. And then we want to find out what is C2 for the frequency 2. Okay. So if you think about it, C is proportional to 1 over F square. And then there is a fixed L. So L doesn't change. So L doesn't change. That means 1 over L is given by, let's say, 4 pi squared. This is the constant. Constant is given by C times F squared. So even though you change the capacitance, L is fixed. So C1 F1, and it's going to be same as C2 F2. Okay. So from this, you get this relationship. Okay, so this is the absolute starting point. This is the starting point, and then you need to know which one is fixed and which one is variable. In this case, L is fixed. C can be variable. Okay, so that in this case, you get this relationship. And then note that F1 is known, I'm sorry, F1 is known, F2 is known, and C1 is known, then you can find out C2. Okay, so once again, I'm just emphasizing that chapter 15 and 16 is actually based off on formula. And you need to memorize formula thoroughly, and then you need to understand what is the number you need to utilize. So that is the main concerns. And then sometimes you need to convert the frequency into radian per second angular frequency. And then you need to think about what is given and what is missing. And then you need to try to find out the missing parameters. But fortunately, all the formulas are relatively simple. So that just sit down and then try to memorize, and then what are the parameters in the formula? Okay, that's the key to prepare your exam. Okay, that's it. And then we'll stop.